When you try to picture nothing, what comes to mind? Silent, dark void, right? It's an absolute emptiness where nothing exists, nothing moves, and nothing happens. For most of human history, that's what we thought filled the vast gulfs between stars and galaxies. But what if I told you that this nothing is actually the most creative and powerful force in the universe? What appears to be a blank canvas is in reality a seething, turbulent ocean of energy. It's called the quantum vacuum, and it's anything but empty. In this realm, invisible fields constantly ripple and fluctuate like an unseen sea. Fleeting particles pop into existence from pure energy, live for a fraction of a second, and then vanish back into the void. It's a relentless, chaotic dance happening everywhere, all the time, even in the space right in front of you. This isn't just a wild theory, it's a cornerstone of modern physics. In the 20th century, brilliant minds like Paul Dirac and Werner Heisenberg realized that space itself isn't a passive stage for reality to play out on. It is a player. The very fabric of space is woven from these dynamic quantum fields. Think of them as the fundamental ingredients of the universe. The electromagnetic field gives us light. The Higgs field gives particles their mass. All these fields, even when they seem quiet, are brimming with latent energy. This vacuum energy has real, measurable effects, subtly pushes on objects, a phenomenon known as the Casimir effect. Imagine two uncharged metal plates placed incredibly close together in a vacuum. You'd expect nothing to happen. But in reality, they are pushed together by the quantum sea around them. The space between the plates restricts which virtual particles can pop into existence, creating an imbalance of pressure from the outside. This isn't science fiction. It's been proven in laboratories. Nothingness is literally exerting a force. But the implications go far beyond that. Many cosmologists believe this vacuum energy is the driving force behind the expansion of the universe itself. This mysterious dark energy, which is causing galaxies to fly apart at an accelerating rate, might just be the energy of empty space. So, the very fate of our cosmos could be dictated by the properties of nothing. And here's the most mind-bending part. Everything you see, everything you are, likely originated from this quantum foam. According to the theory of cosmic inflation, in the first trillionth of a second after the Big Bang, the universe underwent a period of hyper-expansion, driven by the energy of the vacuum. Tiny quantum fluctuations, those little ripples in the nothingness, were stretched to astronomical sizes. These ripples became the seeds for all cosmic structures. The slight variations in density they created were just enough for gravity to grab hold, pulling matter together to form the first stars, galaxies, and eventually planets like Earth. So, look around you. The chair you're sitting on, the air you're breathing. The device you re-watching this on, every single atom in your body can trace its lineage back to a random flicker in the primordial void. We are all, quite literally, made from nothing. The universe didn't just appear in an empty space. It erupted asterisk from asterisk. The emptiness wasn't a void to be filled. It was the fertile ground from which reality itself sprouted. Completely changes how we see our place in the cosmos. We're not just specks of dust in a silent, indifferent void. We are a direct consequence of the universe's most fundamental property, that even in its quietest state, it is buzzing with infinite potential. The fabric of nothing isn't a blank slate. It's the blueprint for everything. To understand the secret of nothingness, we have to travel back to the very beginning, to the moment space itself burst into existence. In the first tiny fraction of a second after the Big Bang, the universe was an unimaginable storm of pure energy. Think of it as a quantum soup, where particles and fields were completely inseparable. The temperatures were astronomical. Space and time themselves were being forged from this raw energy. It was right here in this cosmic furnace that the quantum vacuum was born. Now, in classical physics, empty space was exactly that, empty. It's just a big, boring container for matter and energy, but not an active participant. But then, quantum field theory came along and completely rewrote the rules of reality. According to this incredible theory, every particle you can think of, electrons, quarks, photons, isn't a tiny billiard ball. Instead, it's a ripple, a vibration in a field that fills all of space. The electron field, the photon field, the Higgs field, they are everywhere, all the time. And here's the mind-bending part. Even when there are no particles around, the fields are still there, humming with a faint, constant vibration. This continuous jitter is called a quantum fluctuation. It means there's no such thing as absolute zero energy. Even in a perfect vacuum, energy is constantly flickering in and out of existence. It's as if the universe itself can never truly hold its breath. So, what would you see if you could zoom into this vacuum? You'd witness a relentless storm of creation and annihilation. Pairs of virtual particles, matter and antimatter, spontaneously pop into existence for just trillionths of a second before colliding and vanishing back into nothing. This is happening everywhere, all the time. In fact, it's happening right now in the space between your eyes and this very screen. How is this possible? It's all thanks to the Heisenberg uncertainty principle. Its fundamental rule of quantum mechanics basically says that the more precisely you know a particle's energy, the less precisely you can know how long it exists. This allows the universe to borrow a tiny amount of energy from nothing, create a pair of particles for an incredibly brief moment, and then repay the loan by letting them disappear. It's a cosmic loan system that never, ever stops. But these quantum jitters weren't just some random chaotic noise. They became the seeds of everything we see today. In the early universe, a period of hyperfast expansion called cosmic inflation stretched these microscopic fluctuations across the vastness of space. They became imprinted onto the very fabric of the cosmos. Billions of years later, these tiny, primordial ripples grew into the massive structures we see in the night sky, galaxies, stars, and planets. So, in a very real sense, the reason galaxies exist, the reason you and I exist, is because the vacuum of space is never truly empty. Among all these quantum fields, one plays a particularly special role: the Higgs field. You can imagine it as an invisible, molasses-like field that pervades the entire universe, even in the deepest, emptiest voids of space. As particles travel through it, they interact with this field. Some, like photons, pass right through without being affected. But others get stuck or slowed down, and in doing so, they acquire mass. Without the Higgs field, all particles would zip around at the speed of light. Atoms could never form, matter could never clump together, and our universe would have remained a featureless, glowing mist forever. It's at the Higgs field, a fundamental part of the vacuum itself, is the reason nothing is able to give substance to something. But there's an even deeper mystery lurking within the vacuum. Its energy isn't just a theoretical concept. It exerts a real, measurable force that is shaping the fate of our entire universe. Albert Einstein once proposed something called the cosmological constant, which he initially thought was a mistake. But it now appears to describe a profound truth. The energy of the vacuum itself is driving cosmic expansion. In modern cosmology, we call this dark energy. It's a mysterious, invisible pressure that is pushing galaxies apart from one another and causing the expansion of the universe to accelerate. This means that the emptiest places in space might actually contain the single greatest source of energy in the entire cosmos. It's an astonishing thought that the force determining the ultimate destiny of our universe comes from the energy of nothing. So, we began this journey searching for the meaning of nothing. But what we found instead was a hidden ocean of power, dynamic, restless, invisible fabric that not only fills the universe, but actively creates and shapes it. The vacuum isn't an absence of things, it's the foundation of everything. Every breath you take, every object you hold, every ray of light that touches your eyes, it all exists because of something that isn't really there. The very foundation of all matter lies not solidity, but an incredible emptiness. It's the atoms that make up your body. This chair, this screen are 99.999999% empty space. Yet this isn't a void. It's alive with invisible motion, unseen fields, and boundless energy. It's the quiet hum of the quantum vacuum, the very fabric that fills the entire cosmos. Inside every single atom, particles don't just sit still. They flicker in and out of existence, borrowing energy from the vacuum itself. This isn't some poetic metaphor. It's the bedrock of modern quantum mechanics. When we strip matter down to its smallest scales, we find that particles aren't really solid little balls at all. They are more like ripples, excitations of underlying fields. And these fields, like the electron field or the photon field, permeate all of space. This means that even in the most perfect empty vacuum chamber on Earth, you can never get rid of the fields themselves. Empty space still contains energy. It's still asterisk as asterisk something. This residual energy is known as zero-point energy, the lowest possible state of existence. It's a kind of cosmic background hum that can never be turned off, and it's this very hum that holds the structure of matter in balance, preventing the universe from collapsing into true nothingness. Back in 1948, physicists Hendrik Casimir and Dirk Polder proposed something absolutely astonishing. If you place two uncharged metal plates extremely close together in a vacuum, they should feel an invisible force pushing them together, a push created by nothing. When the experiment was finally performed, the results stunned the scientific world. The plates really did attract each other. It wasn't magnetism. It wasn't air pressure. It was the quantum vacuum itself. The space between the plates had slightly fewer quantum fluctuations than the space outside, creating a pressure difference. This became known as the Casimir effect, and it was concrete proof that empty space is anything but empty. This tiny, measurable force emerges from the random, chaotic activity of what we call virtual particles, particles that pop into existence for fractions of a second. Borrowing energy from the void before vanishing again, it's a whisper from the universe's hidden energy source, a small but undeniable echo of creation itself. Every single second, trillions upon trillions of these virtual particles appear and disappear all around us. You can't see them directly, but their fingerprints are everywhere. In fact, the very stability of atoms depends on their restless dance. These ghostly fluctuations slightly alter the energy levels of electrons in a hydrogen atom, an effect confirmed way back in 1947 in what's known as the Lamb shift experiment. It was one of the first precise proofs that this quantum vacuum energy is real. Without it, the hydrogen atom, the most basic building block in the universe, would not exist as we know it. This same invisible activity gives rise to fundamental constants of nature and even contributes to the mass of protons and neutrons. In other words, most of the mass of everything you see doesn't come from the particles themselves, but from the incredible energy trapped in the vacuum of the quantum fields inside them. Can we harness this seemingly infinite energy? While we can't yet build a vacuum-powered car, scientists have already started to use its principles. Modern quantum electronics like superconductors and ultra-sensitive sensors all rely on the restless energy of the vacuum to control information and current at the near-atomic scale. The Casimir effect itself is being engineered into micro-machines that can move without any physical contact, using the vacuum's pressure as an invisible hand. Even the future of computing depends on it. Every qubit and every entangled photon in a quantum computer is a direct manipulation of the vacuum's hidden structure. Our entire digital future might just depend on how well we learn to navigate the energy of nothing. It gets even stranger. When the universe was born, particles had no mass. They zipped around at the speed of light, completely indifferent to matter or gravity. Then, in a fraction of a second after the Big Bang, a new field condensed out of the vacuum, a Higgs field. It filled all of space, and as particles moved through it, they experienced a kind of drag. They slowed down, they gained inertia, they gained mass. This process didn't add substance to the universe, it added resistance. Matter became heavy, simply because the vacuum said so. When scientists at CERN finally detected the Higgs boson particle in 2012, they confirmed a truth that is both elegant and humbling. The very property of matter, its weight, its presence, its reality, comes from an invisible field filling what we call empty space. We don't exist in spite of the void. We exist because of it. From the smallest atom to the largest galaxy, the quantum vacuum is the silent, invisible thread holding everything together. It gives particles their mass, it binds atoms through its constant fluctuations, and it defines the fundamental laws that make chemistry, biology, and life itself possible. The very ground beneath your feet, the oceans, the mountains. Every living creature rests upon an ocean of unseen energy that is billions of times stronger than all the stars in the universe combined. Yet this energy stays perfectly hidden, balanced in a delicate equilibrium between creation and annihilation. The space between the stars and the space between your atoms are one and the same. The void that connects galaxies also connects the particles inside your own body. You aren't separate from the vacuum, you are a part of it. The same nothing that fills the universe also fills you. Empty space isn't our background, it's our foundation. Matter is just the visible ripple on an invisible ocean of energy. And the next time you look up at the night sky, remember that you aren't looking into emptiness. You're looking into the infinite creative depth of the quantum sea that made you. The vacuum of space, that vast dark ocean we once thought was pure emptiness, is not dead. It's alive. What we call nothing is a constantly shifting landscape of fleeting entities, fields trembling with possibility. It is the stage on which all of physics unfolds. And from this restless sea, a cast of invisible actors emerges. Virtual particles, the Higgs field, and the vacuum energy itself. Each of these represents a doorway into the most profound paradox in science: how emptiness creates everything. In the quantum world, even nothing must obey uncertainty. The Heisenberg uncertainty principle allows tiny amounts of energy to emerge spontaneously from the void. For an incredibly brief moment, this energy forms pairs of particles and antiparticles that appear and then annihilate each other before they can be directly caught. These are called virtual particles. They are ghosts in the quantum machine, not directly observable, yet their presence is undeniable. We know they exist because they leave fingerprints all over the physical world. One of the most elegant examples is the Lamb shift. It's a tiny, almost imperceptible difference in the energy levels inside a hydrogen atom. What causes it? The constant buzz of virtual particles subtly jostling the electron in its orbit. Another is the anomalous magnetic moment of the electron, a tiny deviation from what classical physics predicts. A puzzle solved only by accounting for the quantum fluctuations of the vacuum. Even in complete darkness, these ephemeral beings dance endlessly, their existence written into the fundamental mathematics of reality. They are the constant, invisible heartbeat of the universe. In 1948, the Dutch physicist Hendrik Casimir predicted something extraordinary. He proposed that if you placed two perfectly smooth metal plates incredibly close together in a perfect vacuum, something strange would happen. The sea of virtual particles between them would be restricted, allowing fewer waves of energy than in the space outside. This difference would create a pressure imbalance. The result? The plates would be pushed together, as if nothing were physically forcing them to move. When this experiment was finally tested decades later, the Casimir effect was confirmed. It was a direct, tangible measurement of the energy of the vacuum. It proved that empty space isn't empty at all. It's a physical medium capable of exerting real force. For the first time, the vacuum had become something we could touch. The unseen hands of quantum pressure were no longer just a theory. They were a measured reality. If the Casimir effect shows that the vacuum can push, the Higgs field shows that it can create weight. Discovered in 2012 by the Large Hadron Collider, the Higgs boson was the long-awaited proof of a field that physicists had theorized for decades. It's an invisible, all-pervading field that endows particles with mass. Imagine every particle as a swimmer moving through an unseen cosmic syrup. Some, like photons, glide through effortlessly, which is why they have no mass and travel at the speed of light. Others, like electrons and quarks, have to wade through it more slowly. This interaction, this resistance, is what we perceive as mass. Without the Higgs field, the universe would be a weightless, formless soup of pure energy, expanding forever. There would be no atoms, no stars, no planets, and no people. The discovery of the Higgs wasn't just about finding a new particle. It was confirmation that the vacuum itself gives the universe its substance, its very structure. This leads to the most haunting realization of all. When physicists tried to calculate how much energy the vacuum should contain based on our theories, the answer was staggering. The math predicted an amount of energy so enormous that the universe should have torn itself apart in the first fraction of a second after the Big Bang. Yet here we are. Our universe expands gently, as if the vacuum's incredible fury has been almost perfectly tamed. This staggering mismatch between theory and observation is known as the cosmological constant problem. Our equations suggest the vacuum should contain 10 to the power of 120 times more energy than what we actually measure. That's a 1 followed by 120 zeros. It is without question the most extreme and embarrassing discrepancy in all of science. And yet the tiny, almost negligible remnant of energy that remains, this faint whisper of vacuum pressure is still powerful enough to drive the accelerating expansion of the entire universe. We call this mysterious force dark energy, and it now dominates 68% of all the energy in the cosmos. Even black holes, the ultimate symbols of gravity and darkness, cannot escape the power of the quantum vacuum. According to the legendary Stephen Hawking, something incredible happens at a black hole's event horizon. When virtual particle pairs pop into existence right at this boundary, one particle can fall in while its partner escapes into space. This escaping particle is no longer virtual, it has become real, carrying energy away from the black hole. This process, known as Hawking radiation, slowly drains the black hole of its mass, causing it to evaporate over unimaginable timescales. It means that even black holes glow, all because the vacuum itself never truly sleeps. The boundary between nothing and something has been erased completely. So, everywhere you look, from the depths of intergalactic space to the atoms in your own bloodstream, the vacuum operates as the fundamental engine of existence. It is the powerhouse of creation, constantly converting potential into reality and back again. We stand upon an invisible ocean of infinite depth, a sea whose waves gave rise to galaxies and whose silent hum resonates beneath every single heartbeat. What began as a mathematical curiosity has become one of the most profound truths in modern science. Empty space is alive. But if the vacuum is a living sea of energy, then we must ask, what exactly is it made of? Is it the final fundamental layer of reality, or just another surface, hiding something even deeper, even stranger? The quest to understand nothingness has revealed that it is, in fact, everything. And we are just beginning to listen to what it has to say. What is nothing? It's a question that sounds so simple, almost childish. Yet it has captivated and haunted the greatest minds in science and philosophy for centuries. When we imagine nothing, we picture a perfect void, an absolute emptiness. But when physicists peer into the quantum vacuum, they don't see absence. They see a seething cauldron of activity. When cosmologists observe the vast expanse of space, they see energy appearing as if from nowhere. And when mathematicians lay down the fundamental laws of physics, they find an astonishing degree of order and logic in what should be pure chaos. So we have to ask ourselves, is nothing a real state of being, or is it just a placeholder, a word we use for a profound mystery we don't yet understand? Every scientific theory we have, from Newton's laws to Einstein's relativity, begins with the same quiet, unstated assumption that there is something to describe. But this raises the oldest, deepest question in all of cosmology. Why is there something instead of nothing at all? Think about it. If the universe could have simply failed to exist, why didn't it? Was its existence inevitable? A natural and unavoidable state of reality? Or did something trigger it, a cosmic event, a random fluctuation, a singular choice? Quantum field theory offers a clue. It tells us that even nothing, the most complete vacuum imaginable, cannot be perfectly flat and still. An energy level of absolute zero is forbidden by the laws of quantum mechanics. There must always be tiny, unpredictable fluctuations like ripples on an otherwise calm sea. And it's possible that one of these fleeting quantum jitters was all it took to spark the Big Bang and give birth to our entire universe. In this view, nothingness isn't empty. It's a fertile ground of infinite potential, a cosmic womb constantly birthing universes like ours. To truly understand nothing, we may need to stop thinking of it as a void and start imagining it as a field of endless possibilities. This leads to an even more mind-bending idea, the multiverse. Some physicists propose that the vacuum state we observe, the specific nothing of our universe, is just one of many possible vacua. Each of these different states of nothingness could have its own unique laws of physics, its own fundamental constants. In this framework, the things we take for granted, the speed of light, strength of gravity, the charge of an electron, aren't fixed by some universal logic. They are local bylaws, set by the particular quantum vacuum our universe happened to bubble up from. If this is true, then what we call nothing is actually a vast cosmic landscape, an energy terrain where countless universes are born, evolve, and perhaps die. Imagine an infinite ocean, with our universe being just one bubble in an endless sea of foam. In this grand picture, the laws of nature are not eternal. unbreakable decrees. Instead, they are the outcome of quantum chancerole of the cosmic dice in the primordial sea of nothingness. Our reality is just one of an infinite number of possible outcomes. Yet when our best theories try to calculate the energy of this so-called empty space, they stumble upon a problem so enormous it's been called the worst prediction in the history of physics. Quantum field theory predicts that the energy density of the vacuum should be astronomically high. It's about 10 to the power of 120 times larger than what our cosmological observations actually show. This isn't just a small error, it's a catastrophic failure of our understanding. If this prediction were true, the universe should have been ripped apart by this immense energy, exploding into oblivion a fraction of a second after it began. But it didn't. Against all odds, the cosmos is stable. It's expanding, but at a gentle, leisurely pace. It is balanced on an impossibly sharp razor's edge. This incredible fine-tuning, known as the cosmological constant problem, is one of the greatest unsolved riddles in all of science. Why is the vacuum's energy so perfectly, ridiculously small, yet not exactly zero? Did some other unknown force cancel it out with almost perfect precision? Or does this impossible balance hint at deeper, more fundamental laws of reality that we have yet to even glimpse? The answer to this question could very well determine the ultimate fate of our universe. If the vacuum is a physical thing with energy and properties, then where do the laws that govern it come from? Why do quantum fields exist in the first place? Why do they behave in the specific ways that they do, giving rise to particles and forces? Some thinkers propose a radical idea. Perhaps the laws of physics are not external rules imposed upon the universe. Maybe they are emergent patterns, self-organizing structures that arise naturally from the pure logic of mathematical possibility. In this view, nothing doesn't need a creator or a prime mover. It only needs logic. The late great physicist John Wheeler famously suggested that reality is built on it from bit, that the physical world, the it, arises from information, the bit. Perhaps the universe exists because information itself cannot not exist. Even in a perfect emptiness, logical truths and mathematical relationships would still hold. The laws of physics, then, might be nothing more than the grammar of nothingness, the fundamental syntax of creation, embedded within the void itself. This brings us to another puzzle. If there are infinite universes, each with its own vacuum energy and physical laws, why do we find ourselves in this specific one? The one with constants so exquisitely tuned that stars can shine, complex chemistry can occur, and life can emerge. The anthropic principle offers a potential, if controversial, explanation. It suggests we exist here precisely because only this kind of universe allows beings like us to exist at all. It's a selection effect. We couldn't observe ourselves in a universe hostile to life. In this view, our universe isn't specially fine-tuned for us. We are simply a statistical outcome in a cosmos that produced all possible outcomes. To some, this is a humbling and profound realization. We are not special, but a natural result of cosmic statistics. To others, it feels like an intellectual cop-out, as if nature is dodging the fundamental question of why there is something, and something so specific, rather than nothing. And so, the riddle only deepens, looping back on itself. Pushing to the very farthest edge of speculation, a few scientists and philosophers have wondered if the quantum vacuum itself might be the fundamental substrate of awareness. Not consciousness, as we know it, not thinking or feeling, but the raw, foundational potential for information, for self-reference, for the very state of being asterisk. This is far from proven science. It's a philosophical inquiry, but it reflects a fascinating pattern in our discoveries. The more deeply we study nothing, the more it behaves like something asterisk. An entity with energy, with structure, and, in a way, with a memory of the laws it must obey. Could this be the ultimate origin of everything, a self-organizing, information-rich vacuum giving rise to both matter and mind? In the beginning we thought there was nothing, yet from that supposed nothing, everything we know was born. The more we stare into the void, the less empty it becomes. We've learned that nothing has energy. We've learned that it gives mass to particles. We've learned that it sculpts the grand structure of the universe itself. But the ultimate question remains, is this the final, deepest layer of reality? Or is the quantum vacuum just the surface of something even more profound, a mystery that is only just beginning to unfold? Throughout history, humanity has struggled with the idea of nothingness. What is nothing, an empty void? It's a silent background for something else to exist upon. Or could nothing be the most profound something of all? The scientific journey to understand emptiness has been one of our most daring intellectual adventures. It begins not with the cosmos, but with thought. In ancient Greece, Aristotle denied the existence of the void. To him, nature abhorred a vacuum. Everything had to be filled with substance. Nothingness, he argued, couldn't exist because even to name it gives it being. But another voice, Democritus, imagined atoms moving through infinite empty space. For him, the void was essential. Without emptiness, atoms couldn't move. Without movement, nothing could change. This philosophical duel between fullness and emptiness echoed for millennia, shaping science, religion, and cosmology. Even as late as the 1600s, when scientists like Torricelli created vacuums with mercury tubes, the concept remained taboo. A true vacuum seemed unthinkable till the modern era began to reveal that emptiness was far stranger than anyone had ever dreamed. By the 17th century, Isaac Newton imagined a universe filled with an invisible ether, a cosmic medium that carried light and gravity. For 200 years, this ether dominated physics. It seemed impossible that light could travel through pure emptiness. But in 1887, Albert Michelson and Edward Morley performed one of the most important experiments in history. They built an incredibly precise device to detect the motion of Earth through this hypothetical ether. The result? Nothing. The ether didn't exist. Light needed no medium. Space itself was enough. This null result shattered old beliefs and paved the way for Einstein's relativity universe, where the vacuum was on a static background, but a dynamic fabric that bends, warps, and flows with energy. Einstein showed that mass and energy curve space-time, and that space-time itself can move and stretch. In doing so, he transformed nothingness into something powerful, a geometry capable of shaping reality itself. While Einstein was reshaping gravity, another revolution was unfolding at the atomic scale. In 1928, the brilliant physicist Paul Dirac merged relativity with quantum mechanics. His elegant equation predicted the existence of antimatter and hinted that even the vacuum is filled with a sea of energy and virtual particles. This Dirac sea suggested that every point in space is alive, with invisible particles popping in and out of existence in an eternal dance. Dirac had stumbled upon the idea that would define modern physics, that emptiness itself is a field of infinite potential. But how could this sea remain invisible? Quantum mechanics gave the answer. It exists in perfect balance. For every particle that appears, an antiparticle appears with it, and they instantly annihilate, canceling each other out. The vacuum isn't empty, it's neutral. In the mid-20th century, experiments began to test this unseeable world. In 1947, Willis Lamb measured tiny, unexpected shifts in the energy levels of the hydrogen atom, a discovery now called the Lamb shift. This shift could only be explained if the vacuum itself was interfering with the electron's position, as though the atom were vibrating in the hum of an invisible ocean. A year later, Hendrik Casimir went even further. He predicted that two perfectly smooth metal plates placed in a vacuum would actually be pushed together by vacuum fluctuations. When this tiny force was finally measured, it confirmed what many had suspected. The vacuum exerts pressure. Nothing pushes back, so it was no longer philosophy. It was measurable, real physics. By the 1970s, physicists realized that everything matter, energy, and forces arises from fundamental quantum fields that fill the entire universe. Each type of particle, like an electron, a photon, or a quark, is just a ripple, a tiny vibration in one of these fields. This means that even when there are no particles, the fields themselves remain. Their lowest possible energy state, the zero-point energy, never vanishes. In this view, nothing is in a vacuum at all. It's a set of quantum fields in their calmest ground state. Even that calm hums with infinite energy potential. This realization redefined reality itself. Matter was no longer fundamental. Fields were. And the vacuum, once thought empty, became the stage on which all of existence dances. In 2012, humanity confirmed one of its boldest predictions, the discovery of the Higgs boson at CERN. For decades, physicists had theorized that an invisible energy field fills all of space, the Higgs field, and that particles get their mass by interacting with it. Detecting the Higgs boson, the particle of that field, proved that one of the universe's most fundamental properties, mass itself, emerges from the very structure of the vacuum. The Higgs discovery wasn't just about finding a new particle. It was a powerful declaration that the void is alive. It showed that even the calmest, coldest region of space is a field dense with power and potential. We are not surrounded by nothing. We are suspended within a cosmic field that breathes energy into all things. And yet a great mystery remains. When physicists try to calculate the total energy of the quantum vacuum, the result is absurd, a number so large it has 120 zeros after it. It's a number 120 orders of magnitude larger than what we actually observe in the universe. If that energy were real, the universe would have blown itself apart the instant it was born. This is known as the cosmological constant problem, and it is the single biggest discrepancy between theory and observation in all of science. It tells us that the vacuum hides a deep secret we still don't understand. Some physicists think this secret is connected to dark energy, the mysterious force that's causing the universe's expansion to accelerate. If they're right, then the energy of nothing may be the most powerful and influential force in the entire cosmos. From Aristotle's forbidden void to the vibrant quantum vacuum, our understanding of nothingness has evolved from fear to fascination, from superstition to science. The empty spaces between the stars, between atoms, and even between our thoughts, are not empty at all. They are the very foundation of existence itself.